Welcome, guys. So in this video, we are just trying to prove that the unique factorization domain is basically integrally closed domain. Okay, so remember that we have already proved that the PID, right, is principal ideal domain is a subset of unique factorization domain, and then we have another we will prove today is and then this is a Euclidean domain, and this is an integrally closed domain. Okay, so in order to prove this, let's quickly given the definition. Okay, so the integrally closed domain means that which is a domain, right? But let's say A, and satisfied for all x belongs to A. Okay, so I should say this. I should say if x belongs to the fraction field. So fraction field basically is a divided by b, which b is non-zero, and ab belongs to a. So given an integral domain, one can construct the fraction field. So x belongs to the fraction field, and x satisfy the monic polynomial, and satisfy the monic. Okay, so I should say s is the root. Satisfy the monic polynomial. So which means that x can be written as x to the power n plus c. Let's say cn minus 1 x to n minus 1 to the ceiling c0 equals to 0, where cn minus 1, cn minus 2, c0 are belongs to a. Okay, so if both satisfy this, x satisfy both the first one and the second one, which means that then it will imply x belongs to a. So if a domain A has this property, then we call x is integral closed domain. Or basically, sometimes people use it normal domain. Okay. Okay. So the unique factorization domain, and I think I don't have to define. Basically, you can view x. Any x belongs to A can be written as the some irreducible element, and there's a unit here. So unit maybe, so if you see the really good example is a is the integer, and any number has a prime factorization, except and the unit can be plus or minus 1 when we consider a is an integer. Okay, so theorem is basically says that UFD is the integrally closed. I think this result will use, so usually used in the algebraic geometry. I'm not sure whether abstract algebra use it, but I think this is interesting results. Okay, so proof is very easy. So let's say a is a UFD, and we need to assume that it satisfies the 1 and 2 condition and the integral close, and hopefully prove that x belongs to a. Okay, so we take x belongs to Ka, right? So that means x is just a divided by b, where ab belongs to a and the b is non-zero. And then x satisfies x to the power n, where cn minus 1 x n minus 1 to c0 equals 0. Okay, and put in here that we have a to n, cn minus 1 a and minus 1 b plus c0, b to n is 0. So a plus n can be written as plus b cn minus 1 a and minus 2 cn minus 2 a and minus 2 to c0 b and minus 1, which is 0. Right, so this is some number, right? So which tell you that the b divides a, right? Divides a to the n, right? Right, because if you can shuffle all of this to the right hand side, and you see b divides a, right? But b has a unique factorization. Right, so b can be written as unit of p1 up to pn, right? But that means that means all these prime factor, right, can fall into a. Right, so all prime factors of b will be all prime factors of A, right? Because B divides A to the power n. So which tell you that x equals to A belongs to B. All the prime factor will cancel, right? Except for unit. So finally A belongs to A. So A is integrally closed domain. Okay, that's it. And I will see you guys in the next videos. Be sure to subscribe to my channel.